And now we'll cover what phasors are and how to use them in circuits. So by definition, a phasor is just a complex number that represents the amplitude and phase of a sinusoid. So the definition by itself is unintuitive. So let me just show you how you can use it in terms of circuit elements and circuit variables. So I'll start off by reviewing that Euler's identity tells me that e to the j of theta is simply the cosine of theta plus j of sine theta. And of course, you can also say, well, negative in here, that means it's a negative in here if you wanted to, but we'll just focus on the positive side for now. And if we decided that what we're really interested in is just a cosine of theta, you can simply tell me, well, get the real part of this e to the j of theta. Okay, and if you're interested in the sine of theta, you can tell me, well, just take the imaginary part of e to the j of theta. Plus, minus, it doesn't matter at this point, again. What we're usually given in circuit variables is some sort of a voltage or current. So for now, I'll just assume that we have a voltage, and that voltage were given to me as v of t. It's a function of time, and it has the magnitude or amplitude v of m and cosine of theta, or actually cosine of omega t plus or minus theta. For now, we're going to focus on the theta here and the plus. Okay, and well, what we have now is we have some sort of a cosine. So what I want to do is I want to write it in terms of these Euler's equations. So I'm actually going to utilize this identity in here. So this identity tells me that you can write this as v of m times the real part of the following, e to the j, and then whatever was inside the cosine, which is omega t plus theta. Okay. Of course, we can take the v of m inside, so we can say, well, it's real of the v of m, and at the same time, we can split the e to the j of omega t and e of the j theta. So I haven't done anything, I just did a little bit of algebra. And now I'll rearrange this term, and I can tell you, well, the v of t, which is a function of time, is simply the real part of v of m times e to the j of theta, e to the j of omega t. All right, so this part in here, it's not a function of time anymore. T does not appear in it because t just got in here and that's it. So I can rewrite this part as the following. We can write it as v, uppercase v basically, and we can say, well, v of t is just simply the real part of v times e to the j omega t. And again, just as a quick reminder, what v is just simply v of m. Well, that's a complex number. We can either write it in polar coordinate or exponential. So this is the exponential. The polar coordinate tells me that's basically v of m. The phase angle is just theta. Okay. All right. So what does all of this mean? Well, what it all means is the following. So let me just draw this here. So what I will do is I'll draw this here. Well, I'm going to draw that v. Well, v happened to be here. Okay. Its magnitude in here is v of m, and the phase that we see in here is theta. So what this tells me, well, what originally we got is the following. We got something that has a cosine of omega t and the phi and the v of m. So what we got originally is something that is rotating in here. If you remember, it's like this is our sine or a cosine or something like that. So it rotates, it rotates, it rotates, it rotates, it rotates. Okay, and it has a magnitude of that, and the phase is actually at exactly time 0. This is where we start. Basically, this is at time equals 0. So what is a phasor? Well, a phasor tells me, you know what, let's, I know that the cosine or sine or whatever sinusoid you're looking at rotates, and if I assume that this omega is just a constant frequency, the frequency doesn't change with time, that's what we have in here. The frequency is not a function of time. If it's rotating at 60 hertz, it's rotating at 60 hertz or something like that. Or like omega is in radian per second, like 60 radian per second or something like that. So how about I drop this one in here and I tell you I'm going to imply it. It's not that it disappears, it's just going to basically be implied. So what I have done is I have done the following. I started with v of t is just a function of time, which is just simply v of m cosine omega t plus theta, and what I ended up with is the following. I ended up with just a phasor representation of this voltage, okay, and this phasor representation tells me that simply v, which is a complex number, is v of m and the phase angle is theta, and it doesn't contain time now. So what I have done is I actually converted from a time domain, this is a function of time, to not a time domain, what we call a phasor domain. So I converted an input that is sinusoid into what we call a phasor. Again, the phasor representation just simply tells me here's the magnitude, here's the theta, and it implies it's rotating omega t in the time domain. That's what it implies. But because that's simplification, I basically can convert it. And the conversion, as you can see, is pretty straightforward. All you have to do is take a look at the Vm and the theta, and that's it. Okay. All right. So now we have our time domain representation and our frequency or phasor domain representation. This is how we convert voltages or currents within a circuit. So we start with the time domain, we convert it to the phasor domain, and then we do our own things in the phasor domain and come back. So can we come back in here? Yes, you can. It's simple. All you have to do is just tell me, well, multiply the V of m times the cosine. Well, let me just officially or represent it. So if you want the V of t, you can tell me it's simply the real of whatever V you got times e to the j omega t. You have to multiply by j omega t and just take the real part. And of course, this is the real of the V of m theta. Well, the coordinate, the exponential is j of theta, j of omega t, e to the j omega t, sorry. And of course, hopefully you understood that this is basically Vm of cosine omega t plus theta. All right, so the conversion between the two domains is pretty straightforward. So we have V of t. If I've been given that V of t is cosine omega t, okay, plus theta, and I told you go to the phasor domain, you can tell me, well, the phasor domain is pretty straightforward. It's just simply V of m, that's the magnitude, and theta. That's it. If I told you, well, go back, what you do is you tell me, well, okay, all I have to do is just stick the V of m in here, put a cosine and the omega t. I have just to know what omega is. This is based on a fixed omega. All right, so a few comments in here. So this one here is what we call the time domain. Okay, so I'm gonna write this here in the same color as the blue in here. So this is time domain. Okay, this is, on the other side here is what we call a phasor domain. Okay, so why am I writing it this way? Because you need to distinguish that V of t is a function of time. V is not a function of time, so there's no time in here. So let me just write that here. So there's no time in here. There shouldn't be any representation of time. So time nomenclature shouldn't appear in the phasor domain. So if you convert a circuit into the phasor domain, I shouldn't be looking at the t anymore. Okay, so this one here, the numbers here are all real. There's no complex whatsoever. In here, generally, they're complex. And I'm saying generally is because sometimes what you get with the phasor domain is the VMM is some sort of a value and theta happen to be 0. Well, if the theta is 0, that means this is also a real number. But generally speaking, you'll get a V of m and a theta. So this one here is complex number, this one here is a real number. Okay, so again, the representation or the way you convert it is when the omega is just fixed. So if you have different omegas or like you have different sinusoids rotating at different omegas or different frequencies, you won't be able to apply phasor domain directly. You have to use some other thing, which is superposition. And one last comment, if when you do these phasor transforms, I have explained it to you with a cosine, but sometimes what we have is we have, instead of cosine, we have a sine or maybe a negative sign or something like that. So by convention, it tells me that convert all the sinusoids you have into a positive cosine and then do the transform. That's by convention. You don't have to follow this convention. You can convert all of them to positive signs, for example, and do that. But by convention, whatever, like if you have like some sort of a sinusoid in the time domain, just make sure it's in the positive cosine and then do the conversion. That's the convention. All right, so a few more things in here. So I'll talk about what we call a phasor diagram. Okay, so phasor diagram and diagram. So what does it mean? Well, a lot of the times we end up with a circuit that contains the following. I tell you, well, the voltage across some sort of an element happened to be V of m cosine of omega t plus theta, I'm going to call it V in here. And at the same time, you computed the current, and the current happened to be, this time it's actually I of m, and it happened to be cosine of omega t, the same frequency, and it happened to be that it's negative I. And I tell you, let's compare the voltage and the current together. So what you do is you convert them to phasor domain. So in phasor domain, this V of t becomes V. So uppercase usually represent the phasor domain, lowercase represent the time domain. Okay, and then you can tell me that this is V of m and the angle is just theta V. And this one here is I, and this is I of m, and the angle is negative theta I. And now we can plot these two in here on a diagram in here. This is what we call a phasor diagram. So in the phasor diagram, what we have is we have the following. So I'm going to do this here, and I can tell you that this is V of m, and from here to here happen to be theta V. And from here to here, what we get is maybe I of m. They don't have to be the same magnitude, and this one here is negative theta I. And we know from phasor definition that both of them are be rotating here in this particular direction at the same frequency. So if this is rotating at the same frequency as that, so the relative location of V versus I will be the same. Again, this one here is simply, this is what we represent as I, and this one here is what we represent as V, complex numbers. So since they're rotating at this particular location or at this particular speed, what I can say is the following. So V is leading, okay, I. That's what we can say. It's in a leading direction because V happens before, because it actually hits the 90 degrees before the I hits the 90 degrees because of the way they're rotating. So we can say that V is actually leading I. By how much? Well, the angle difference is the following. Theta V minus, it happened to be negative theta I. That's basically, so V is leading I by this particular phase angle difference. Sometimes what I can say is I is lagging behind V with this. Now, the other thing that you need to understand that whatever you go in here, this is basically the lag direction. So this is the lead direction. So whatever you see in here is leading, whatever in here is lagging. Again, all of these depend on the fact that we're dealing with cosines in here and they're rotating at the same exact frequencies. All right, so I wanted to also give you an example of how we can use phasors. So let's assume that for some reason or another, you got a circuit, and in that circuit, you got a couple of voltages, V1 and V2, and you were told that the V1 is represented as a negative cosine, blah, 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 and V2 is positive sine. And you were told, like, let's move both of them to the phasor domain and identify which one of them is actually leading. So again, convention says the following. First, we need to convert everything to cosine, but before we do the conversion, I need to make sure that both of them are actually operational at the same frequency, and they are, because if they're not, you cannot compare them, because one will be rotating at a faster speed than the other, so the phase difference and everything will change with time. So both of them have an omega of 300, so we're okay that way. So what we need to do is we need to make sure to convert V1 into positive cosine that's in the negative and this in the negative sign. So just the graph in here, just very quickly, this is cosine, sine, and this is negative cosine, and this is negative sine. So what I'm after is actually going from a negative cosine to a sine, so all I have to do is just add or subtract 180 degrees. So V1 of t is just simply 15 cosine 300t, and I'll add the 180 degrees, okay? And those here together, basically 180 minus 25 is 155 degrees. So let me just write it in here just to save a little bit of space. So that will become positive 155 degrees. That's what it is. All right, what about the other phasor? Well, this is not a phasor yet. We're still in the time domain. So V2 of t, well, what I need to do is I actually need to go from sine to cosine. So I need to subtract 90 degrees in here, okay? So we're going to do 15, oh, this is not 15 now. It's 10 cosine 300t plus 105, and then degrees minus negative 90, or minus 90 degrees. And this happened to be exactly 15 degrees. So let me just write this here, okay? So this will be 15 degrees. All right, so we have both of them now in the time domain represented as positive cosine. So all we have to do is to convert them into the phasor domain. So the phasor domain representation for V1 of t is uppercase V of 1, and this basically the magnitude is 15, and the phase angle is 155 degree. This is how simple the phasor transform is. And V of 2 is equal to the 10 and 15 degree. So now we have both of them in that particular representation, and hopefully you can figure out that, well, V of 1 is actually leading because 155 versus the 15. But you can also plot it in terms of phasor domain representation or phasor diagram. So we have the first one is actually at 15 degrees from the cosine. So this one here is 15 degree. This is basically V of 2, and the other one is actually 155. So 155 minus 15, so it's about 140 degrees. Like, it's not up to scale, but from here to here it's 140 degrees because this is the phase difference between them, and that's V1. So V1 is leading, and specifically it's leading by 155 minus 15, which is 140 degrees. Okay, so it's leading by 140 degrees. Now, another more interesting thing is, well, what if for some reason or another you're writing some sort of an equation and you needed to add these two voltages? Well, adding the voltages in the time domain is really annoying because you're adding a couple of cosines and they have different phases, different magnitudes. But in the phasor representation, it's much, much easier. So here's how we do that in the phasor representation. So if I told you V1 plus V2, well, you can tell me it's 15 155 degrees plus 10 and 15 degrees, and you can use your calculator to tell me what the answer should be. And what you will get is the following: 9.76, and this one here is 113.79 degrees. Okay. Again, you do not add the phases in here, okay, because you have to convert them to rectangular coordinate and add them and then convert them back. But if you use a calculator, you should be able to get that number directly. But more interestingly is the following: I can represent this one here as v1 of t plus v2 of t by doing an inverse phasor transform at this point. And an inverse phasor transform tells me this is 9.76, this is magnitude of that sum, cosine, well, the omega, both of them share the 300 times t, and now the phase is 113.79 degrees. So look what we have done. What we have done is that we added a couple of the sinusoid without having to do any trigonometry. So we moved to a phasor domain in here, so we represent both of them in phasor domain representation. We did the addition as complex numbers, we get that one here, and then what we did is we did an inverse to get back to the time domain, and in the time domain we got the t back. Again, there's t in the time domain, no t in the blue in here. There's no t in this side at all. But then when you convert back to the time domain, you'll get that t in here. And coming from here to here was much easier than doing it in the time domain.